Hello everyone. In this video, I'll be discussing about logistic regression. So the whole discussion is divided into four parts. In the first part, I'll be discussing about what is known as logistic model. Okay, and I'll introduce the terminology in logistic regression. Okay, and then also loss function. So second, I'll discuss about stochastic gradient descent. Which is shortly called as SGD. Okay, we call shortly logistic regression here as ELR. Okay, so the stochastic gradient descent we discuss because we aim to find the weights of the logistic regression. So the third section is about computation of weights in the logistic regression. Okay, and the fourth one is about reasoning for using a particular loss function in logistic regression. Okay, there we can use many loss functions, but a particular loss function is being used in this uh, video or in this topic. Let us know the reasoning why we use that particular loss function. Okay, so yeah, these are the four broad categories which have split the discussion into. So let us start the logistic start from the first thing, which is about logistic model, terminology, and loss function. So before discussing this, I want to say that most of the content which I discuss in this video is from the Andrew Ng's lecture from the Coursera courses. So, and I'm doing this video for the machine learning course of Yale University. So let us start with the model. So logistic model. So logistic model is a statistical model which is used to find the probabilities of classes, or which is used to model the probabilities of classes. And in the logistic regression, we aim to compute the weights which are present in the logistic model, and the procedure to compute the weights and the mathematical derivations, all those things would be discussed in this video. So first let us get introduced with the basic model and see what are different terminologies which are involved in the logistic regression. So yeah, consider an input x1. So I'm assuming the input is of dimension n. So let me say x2 and so on until xn. So this is one, this is, so we have this, and consider here, so x1 multiplied by w1, or the weight is w2 wn. So here you have inputs of dimension n, and associated weights are notated as w1 to wn. So the first operation is to multiply the inputs with the weights, and later you sum all the products. So it is like a sum of products operation, and then you pass through a non-linear function which is here called as sigma. So sigma is a nonlinear function, or here it is a logistic function or a sigmoid function. I'll discuss about that, and what you get output is a probability of a particular class. Okay, so since logistic regression falls under the category of the supervised machine learning algorithm, we assume that we have the input data with its corresponding labels, and so here I'll be restricting in the I'll be restricting to binary classification. So I consider that there are two classes. So y belongs to either 0 comma 1. okay, any of these particular classes, and input belongs to any of these two classes. And we let us first discuss now what is this logistic function. So logistic function, so logistic function, also called as sigmoid function or a S-shaped curve, is a continuous approximation of a step function. So it looks something like this. So you have, it starts from minus infinity and slowly it reaches 0.5 at 0 independent, and later it saturates at 1. Okay, and as it acts like, so this x is equal to y is equal to 1 acts like an asymptote for this function. And so we have at here it is 0.5, and this is a sigma of, say you have an independent variable z. Okay, so z is an independent variable and sigma is the non-linear activation, non-linear function, which is called as logistic function or a sigmoid function. So the mathematical expression for this function is 1 by 1 plus e power minus z. Okay, so let us consider it as f of z. So f of z is equal to 1 by 1 plus e power minus z. So this is the logistic function. And so we multiply input with the weights and we sum all the products and later pass it to the logistic function, and that will result the value in between 0 and 1. So the values which we obtain are considered as probabilities. So let us see how we can uh, understand the output. Let us see how we can assume the outputs. So as I've said, the the outputs are probabilities. So here we define the output as follows. So what we say is, so probability, so we aim to find the probability of the classes for a given input x. Okay, x is a vector, so for a given input x, what is the probability that this class belongs to the class 1, and we define this as y cap, and its corresponding opposite, which is y is equal to 0 for a given input, is treated as 1 minus y cap. So here I am assuming as a binary classification problem. So if it is a if it is a multi-class problem, or if it is problem which is of having classes more than two, then we can categorize, we can have a multinomial logistic regression. So here we are restricting it to binary logistic regression. So we assume 0 or 1 as the class information. So now we have defined what is the output in the logistic regression. Now let us see how we can, how, and we also need to know the terminology of representing different input data. So I have said that x is a n-dimensional data. So for a ith data, so it would be this is the ith input and its corresponding ith output, which is the class information. We can consider it as an ordered pair. So we assume that we know this input data, or we know this input data with its class information in a supervised learning algorithm, in a supervised logistic learning algorithm. So our goal, our job in logistic regression is to compute these weights. So I have missed one point. You can also consider a bias b with input 1. So if there is no uh, value, you can consider the input as 1. So that would be much more generic. So here, so I can also write here. So yeah, let me write it here. Anyways, I'll be doing it later. So this is the ith data point. You have the input vector xi and its corresponding class values, which is yi, and whereas y cap here is the estimated or the computed value. So let me write it here. So y cap is the computed output, and y is the actual label class label. Okay, so here we are assuming it as binary classification, so it is either 0 or 1. So yeah, now let us define what is loss function with the computed versus the actual class value. So here you can consider as say you are trying to define for the ith input data. So let me consider this ith value. So here the loss function we define as follows. The reasoning for choosing that particular loss function is discussed in the part 4 of this video. So first let me write the loss function. So before that, by usually we use a loss function which is called as mean squared error, which is the difference between the actual computed value and the actual value, and take the square of it and take a mean of it. But whereas in logistic regression we use a different type of loss function, which I would write it here. So let me move this here. So the loss function is something like this. So you have minus yi, so I is the ith, so I'm just writing in the top, log of 1 minus, sorry, log of yi cap minus yeah, once again, 1 minus yi cap, so there is no need of cap here. Yeah, 1 minus yi into log of 1 minus yi cap. So this is the loss function which we use in logistic regression. So and there is also a term called cost function. Okay, y cap comma y. So I'm not writing here ith because it is using all the input data, all the input and all the output data. So here it is like I is equal to 1 to m, 1 by m. You have loss function yi cap comma yi. So you're summing up, you're taking the average of all the loss function values computed for each and every data point. So this is this particular part discusses the all the terminologies, notations which we use in logistic regression. So in the next part we would be discussing about how to compute these weights, and first, before going to the computation of weights, I'll discuss what is called a stochastic gradient descent algorithm, and then we will be going for the computation of weights, and later we'll discuss why we have used this particular loss function and not any other loss function. So let us start with the discussion about stochastic gradient descent. Let us see how this is used in logistic regression. So as I've said earlier, we would be using SGD for computing the weights. So let us first discuss the details of SGD, and later in the next part we will see how SGD would be applied to in the computation of weights. So yeah, let us start. So let me first draw a function which I will be using for explanation. So consider any function. Let us consider a simple parabolic function. Okay. So say you have this as a some notation. You can use it. Say 3 points. Okay. Say this point is A. Say this point is B, okay, and say this optimum or the point at which the minimum is C. So this is a nice parabolic function. So stochastic gradient descent algorithm works in the following way. If at all, if you have a function f of x, say x is a independent variable, and you aim to find the value or the point where it has a minimum. So the method in stochastic gradient is to keep on change in the direction, start from a random point, it can be anything, and keep on moving the direction uh, opposite to the tangent. Let me describe that neatly. So here, suppose you want to reach to the optimum value, say x star, and you have started with point A. As you can see here, the slope at point A is negative. So the slope is negative here. The slope at point B, as you can see here, which is positive. Slope, the tangent or the tangent gives the slope. So the tangent here is positive, the tangent or the slope here is negative. So our goal is to find this point. So as you know, the point at which we have a minimum, we have the slope as 0. So we need to reach to a point where the slope is 0. That is why when we use when we want to find a minimum point, the point at which we have minimum for a function, we generally differentiate and equate it to 0 and find this point. So that was a normal procedure, but in stochastic gradient descent, what you generally do is you keep on move to a new point x. Say suppose if you are at a point xi, so the new point xi plus 1 is equal to xi minus alpha into delta x. Okay, so what does this mean, why we are using this negative sign, and what is this delta x? So delta x is nothing but it's differential with respect to the function f of x. Okay, and alpha is the learning rate, the weight, or you can say the alpha is the step value, the way, the amount of fast, the rate at which you are choosing the step size. So that is denoted using alpha. So delta x is dou f of x by dou x. What does this mean? So suppose if you are at a point x, I say a, and we would be moving in the direction, or we would be computing the next point of x using this following equation. So it says that delta x is nothing but the slope of the function. So whatever is the slope of the function, append a negative sign to it. So this learning rate, the alpha is always positive, so it determines the step size. So suppose if delta x is negative, as in the case here, slope is negative. So if the slope is negative, this overall term would be positive. So if the overall term is positive, you are adding a value to xi, so it increases the value, so it moves in the direction where the xi value increases, so it moves closer to C. Suppose if you have chosen the random point as B, so here the slope is positive, so slope is positive means this is positive, and this overall term you have a negative term, so whatever may be the xi value, so from there it would subtract and you would once again reach closer to C. So irrespective of where you start, it will always tend to move in the direction where we have the minimum point. So that is how the stochastic gradient descent algorithm works. So we have to see now how we can utilize these to compute the weights. So we have a loss function in our logistic regression, which is notated as L of yi comma yi cap. So our goal should be to differentiate tau L by or find the weights. So usually when we start with the initial value, that usually we choose a random value. So for example, you start at A some random value and keep on move closer to C. So once you get the xi plus 1, use that and compute the next xi plus 1, and you keep on move until you reach to a minimum point. That is the main logic in SGD. So here, so the same thing when we applied for the logistic regression, our goal would be to compute weights in wi plus 1 iteration using the wi iteration minus some alpha into delta w. Okay, here delta w is nothing but dou L divided by dou w. Okay, so this is what we aim to find, so that we get we do this number of iterations, so that the final w value would be same as the optimum value. So we are supposed to compute this dou L by dou w. So this is our goal. In this we will be using in the derivation of derivation of computing the weights in logistic regression. So let us see how this can be derived in the next part. So broadly what I have discussed here is we have discussed what is known as gradient descent algorithm, and we have seen how you can reach to the optimum point by using this equation. So what we need is this differential, and so here it is a simple one-dimensional function which I have taken, but most of the time it would be a vector. So we have to appropriately differentiate with the corresponding variable so that we get the proper gradient, and later we compute the weights. So let us see that in the next part. So let us continue from where we have left in the previous section. So in this part we will see how stochastic gradient descent is used to compute the weights. So first, before that, let me once again draw the logistic regression, and the diagram correspond to the logistic regression, so that we can proceed with the computation of weights. So we have input multiplied by weights. One second. So input multiplied by weights, so x1 multiplied by w1 and xn multiplied by wn, and there are intermediate inputs. So we pass it to the logistic function, which is sigma, and whatever we get is y cap. Or so I use a notation here. So I will consider this as ai. Whatever for input xi, whatever we get is considered as ai. I'll also be using the same notation here, yi cap as ai. I'll be using two notations. yi cap is what we have defined in the loss function, and ai is what I'll be using here. So this is just to be in synchrony with Andrew Ng's lecture. So let us compute intermediate components. So I'll denote the summation, sum of products, as zi. So let us put I in the subscript, because superscript, because that corresponds to the ith input. So zi, I'll define it as sigma wi wj xg. Okay, and j is equal to 1 to n. So this is how xi is a notation. So this is how zi is defined. So it is a summation of all the inputs, it is a product of all inputs and the weights. and we sum all those things. So we have the sum of products term. So sigma of z, as we have seen earlier, will be defined as follows. So sigma of zi for the ith input can be defined as 1 by 1 plus e power minus zi. So our goal is to find out, so as I have said in the SGD, our goal is to compute, so let me write the rest of the things here. Our goal is to compute dou L by dou W. Okay, so L is the loss function, which is a function of yi and comma yi cap. So this is a function of this. So to find dou L by dou W, what I'll do is dou L divided by dou Z or dou AI and dou AI divided by dou ZI into dou ZI divided by dou W. So here I am just using partial derivatives. We all know if a function of function f of g of x, something like that. So we have, if you have a dou L by dou W, and if L is a function of yi, and we can use this splitting in of partial derivatives to compute the dou L by dou W. So let us find out each and every component, and in total we will find out dou L by dou W. So first dou L divided by dou AI. This is what we are supposed to find out. So first of all, L, will let us write it here once again, log of, okay, sorry, L is defined as yi minus yi log of 1 log of yi cap minus 1 minus yi into log of 1 minus yi cap. So this is how we defined earlier as loss function. Now when you, as I've said earlier, yi cap and ai is ai are similar. So let me replace that here. So dou L, so it would be, yeah, first let me write L in terms of ai. So L would be minus yi log of ai minus 1 minus yi log of 1 minus ai. So this is what is the loss function. Now let me compute dou L divided by dou ai, which would be minus yi. So the differential of logarithm would be 1 by ai. So I'm assuming it is a natural logarithm here. So ai minus 1 minus yi divided by 1 minus ai. So this is what we got. Now let us, but so this is what is dou L by dou ai. So let us keep in some bracket. Yeah, this is the first one we found out. This, let us find out the rest of the things. So the rest of the thing is to find out dou ai divided by dou zi. Okay, so we know ai is nothing but the sigmoid function, which is 1 by 1 plus so sorry, so ai we already know it. So first let us write it a sigma of zi. Sigma of zi is nothing but ai. So ai is nothing but 1 plus e power minus zi. So now dou ai divided by dou zi is nothing but So differential of these, you can also write this function as e power zi divided by 1 plus e power zi. So let us differentiate this. So 1 plus e power zi into differential of e power zi is e power zi minus e power zi into differential of this is e power zi. So divided by 1 plus e power zi whole square. Okay, so let us keep this all in under one segment. Yeah, let me erase this, it's not looking good. Okay, now we got this. Let us simplify this. So that implies so we have here e power zi, which we can take it as common. So e power zi into 1 plus e power zi minus e power zi. So it would be just 1 divided by 1 plus e power zi whole square. So this is the differential. This we can write it in this form. So e power zi divided by 1 plus e power zi is nothing but ai, and 1 by 1 plus e power zi is nothing but 1 minus ai. If you do 1 minus ai, you get 1 plus 1, 1 by 1 plus e power zi. So you have 1 minus ai. So this is what is the final expression of dou ai divided by dou zi. So that would be ai into 1 minus ai. Okay, let us compute the third component, which is dou zi divided by dou w, and let us multiply all together, and we would see later we would get a very simplified expression, or else let me write it here itself. Okay, so this is one segment. Let me put it under one category. So, and let us highlight this. Yeah, we got dou L by dou AI, dou A by dou ZI. Now let us find out the third one, which is dou ZI divided by dou W. So this we have to find out. First, let us write ZI. So what is ZI? ZI is nothing but sigma W J X J I. So you can also include B, which I haven't done earlier. Sigma plus, you can also include B. Okay, so let me give it here. So B. So when we find dou zi divided by dou w, which would be, say I want to find out for dou z, that would be xj I. So this is the derivative, this is a constant, so it would be 0. So now after finding out all these things, dou L divided by dou W, which is equal to, so let us discuss, let us continue with dou L by dou Wj. So as you can see here, we have computed all the three terms. So let us go with dou L divided by dou W, which is equivalent to dou L divided by dou AI, and dou AI divided by dou W, dou Zi, and dou Zi divided by dou W. Okay, so let me clear all these things. Okay, so as you can see here, we got all these three terms. Now a small correction here. So I have adjusted here. So when we differentiate logarithm, we get 1 by 1 minus ai, and we get a negative term from here. So I've just introduced this negative term, and I've just simplified in this form. So when we simplify, we get ai minus yi divided by ai into 1 minus ai. So we'll use this simplified term dou L by dou ai and into this expression compute the final expression. So let me write it in the same fashion, dou L by dou w. So okay, dou L by dou ai is nothing but ai minus yi divided by ai. Okay, let me increase the thickness. So ai into 1 minus ai. So this is what we get from the first term. Second term results in ai into 1 minus ai. Okay, and the third term results in xij. So this all corresponds to dou L divided by dou Wj. So let me also write it here. We are trying to find dou L divided by dou Wj. So as you can see, this can be cancelled out. So what we are left with is ai minus yi into xij. So dou L by dou W has been simplified to a small term which is ai minus yi into xij. So this is an important equation which we will be using in SGD. Okay, so we used SGD, we use this particular term in SGD. So let us see how we will use. Before that, we also need to compute the differential with respect to b. So let us write that. So as when we differentiate with respect to b, in place of wj, we don't have any term here, so it is 1. So what we get is a constant term. So I'll write it here directly. Dou L by dou b is nothing but ai minus yi. Okay, we don't have any xij term. So this is the second equation. So both equations are very much needed and very much useful in logistic regression. So let us yeah, let us start now how this can be incorporated into stochastic gradient descent algorithm. Okay, so SGD, as we have already known SGD, the equation to find the uh, I. So the equation to compute weights is through as follows. So Wj plus 1 is equal to Wj minus alpha into delta W. Delta W is nothing but dou L divided by dou W. So we got dou L divided by dou W for any J, any W. We have n such weights. So in the same way, we have one scalar bias. So all these things can be incorporated and into this expression of SGD. Let us do that. So when we incorporate, Wj plus 1 would be equal to Wj minus alpha into ai minus yi into xij. Okay, this is one, and bj plus 1 is equal to bj minus alpha into ai minus yi. So these are the two expressions we use. We will keep on iterate many times so that we converge to a stable values of weights and stable values for p. So this is how we compute the weights in logistic regression. So so this is the derivation. It's a very easy, not too complex, as we have seen that how what is a logistic function and how to compute dou L divided by dou W. In the previous section, we have seen why we need that. In the stochastic gradient descent algorithm, the update equation needs the gradient term. So the gradient terms are computed in this particular section. So this is what we got dou L by dou ai when we differentiate, we got ai minus yi divided by ai into 1 minus ai. So this is getting cancelled out with the term dou ai into dou zi. So it got into a very simplified form, which is ai minus yi, and you have this extra term which is a result of dou zi divided by dou wz. So in this way we compute the gradients and we introduce this gradient into the SGD expression, update expression. So alpha is a step size, alpha determines the step size, and it is heuristically chosen. So this is how we compute the weights in logistic regression. So in the final part we will see what is the reasoning behind using a loss function which is defined here. Why not any other loss function like a mean squared error or any other loss function? So let us see in the next part. Hello everyone. Today we'll see the fourth part in the logistic regression discussion. So in this part we will discuss about the reasoning for using a particular loss function. So we have seen the loss function which we have discussed in the previous section. So this is the loss function, and let us see why this particular loss function is being used and not any other function. So because so let us start the discussion, start the lecture. So let me write the equation first here. Loss function. So loss function L of yi comma yi cap is given as minus of uh, yi log of yi cap. So wherever there is a cap, it's a computed one. Yi is the original class value, and 1 minus yi log of 1 minus yi cap. So all these logarithms are natural logarithms, that is to the base e. So this is the loss function, and we aim to reason out why we are using this particular loss function. So first let us revise some of the terminology of y cap. So we defined y cap in this manner. So if the class is for class 1, for y is equal to 1, we have probability of y is equal to 1 given x is equal to y cap. So this is how we have, and for y is equal to 0, we have probability of y is equal to 0 given x as 1 minus y cap. Okay, so here we have two expressions. So we would like to write both these expressions into a single expression. So we want if we want to write, so since we as have already assumed that we are particularly focused on binary logistic regression, so I'm assuming that there are only two classes, 0 or 1. So if I want to write it in a general way, probability of y given x can be written as, so we have to merge these two equations into a one equation. So how can we do that? So there is a one beautiful way to do this. So let us discuss that first. So here, so this, let me write this. These are all small letters here, and here the x is input vector, y is the class label for that input vector. So we can be more specific here: xi, yi, yi. So you can also write yi here. So this, so that it becomes uh, specific to one particular example, ith example. So now when we are looking for probability of ith example given an input vector xi, we can write it in a single expression as follows. So it would be yi cap to the power of yi 1 minus yi cap to the power of 1 minus yi. So this whole thing, these two expressions can be written as in a single expression in this manner. Let us see why we can write it. For example, take yi is equal to 1. So if it is 1, this is 0, so this term would be 1. So if yi is equal to 1, so what is happening? We have here, we are left with yi cap whole power 1 and 1 power 0. So this will be yi cap. So that is what we are getting here. And if yi is equal to 0, then we have, if you substitute yi as 0, so this would be 1 and yi is equal to 0, so you'll be getting 1 minus yi cap. So let me write it here. So this yi cap power 0 into 1 minus yi cap power 1 minus 0 1. So this, so you will be getting 1 minus yi cap. So writing in these two steps or writing in this one single step is nearly same. So that is how we brought into a single expression. Now let us see, we got in until here, we got the probability of the ith example for a given input xi is expressed as this man. So let us see how this how do we get the loss function and the corresponding cost function. So first let us take the logarithm on both sides. So log of probability of yi given xi is equal to, you will be getting yi log of yi cap plus 1 minus yi log of 1 minus yi cap. So this is what we got. And suppose if you assume all the inputs as independent, and if you assume the independence across different examples, then the total probability can be written as the product of individual examples probability. So let me write that. So the total probability I is equal to 1. Consider that there are m examples. So okay, if there are m examples, we can write this as probability of y given xi. So this thing can be we would like to maximize this probability. See, our goal in logistic regression is to find the probability of a particular input belonging to a class. So we always try to maximize these particular probabilities. So maximize this probability, this is equivalent to maximizing, so logarithm is a monotonic function, so if you maximize these or maximize uh, maximize this function, it would be the same thing. So maximizing log of probability of yi given xi, both are same. And this is once again equivalent to minimizing the negative log of probability of yi given xi. Okay, and so when you convert product, when you take the logarithm, you get summation here. So I is equal to 1 to m, and yeah, let me write it here once again, summation. So you get this summation I is equal to 1 to m and negative log of this thing. So we aim to minimize negative logarithm of the probability, and that is how we get the expression for the loss function. And this here, since it involves I is equal to 1 to m, we can bring this and minimize each individual example. So this is the reasoning for why we use a particular why we use this particular loss function. So let me, yeah, minimize minus log of probability of yi given xi. So this is the reasoning, and we individually use it, and later we can sum it up for all the values. So yeah, so these are the four parts of the logistic regression. We have seen the model, terminology, loss function definitions. We have seen what is stochastic gradient descent. We have seen how weights can be computed using stochastic gradient descent, and we have finally seen the reasoning for why we are using this particular loss function. I hope it would be helpful for everyone, and here I end my video.